Core Principles for Building Neural Networks on Gradients, Domains, and Nonlinearity. In this talk, you will come to understand deep neural networks more deeply. If you currently think of deep networks as a black box that sometimes produces magical results and sometimes fails mysteriously, this talk will bring a good amount of clarity. You will learn key principles for building neural networks. The insights we present can significantly reduce the amount of manual design effort and trial and error necessary to build a high-performing neural architecture. Finally, you will get an introduction to the exciting field of deep learning theory. If this talk sparks your interest and you want to dig deeper into neural network design, I recommend you read the publication that this talk is based on, named The Exploding Gradient Problem Demystified: Definition, Prevalence, Impact, Origin, Trade-offs, and Solutions. It is freely available on archive.org. The link is shown here and is available in the description of this video. I will present an earlier version of this publication at the 2018 installment of the International Conference on Learning Representations. The talk also draws from a publication that is currently under development and is scheduled to be released in May 2018. Upon release, the link to this publication will be added to the video description. Finally, other references as well as hyperlinks that take you directly to specific sections of this talk can also be found in the video description. When it comes to the topic of neural network design, there is a wide range of divergent opinions. Anyone who has spent a good amount of time around deep learning researchers or practitioners is likely to have encountered some of these four statements, or indeed their complete opposite. One view of neural network design is encapsulated in this cartoon. At the top, it shows the classical view of the behavior of machine learning models. It then juxtaposes this with a hypothesis about the behavior of neural networks. The classical view, of course, is that as models become more complex, they eventually start to overfit. In contrast, this cartoon posits, when layers are added to a deep neural network, without much thinking and without much design effort, we can expect the performance of the model to get better and better. The classical view could be encapsulated in this well-known graph, where the model complexity is shown on the x-axis. The training error is getting better and better as the model complexity increases. In contrast, the test error gets better initially, but then beyond a point gets worse again. Of course, one of the key goals of model selection is to find the sweet spot here, where the test error is minimized, so as to avoid the region of overfitting on this side, as well as the region of underfitting on this side. The view that the cartoon posits about neural networks can also be encapsulated in, for example, this graph here. This slide shows a screenshot taken from a video on Andrew Ng's YouTube channel. This is a graph that he likes to show in many of his talks. One of the implications of this graph is that no matter how much data is used to train a neural network, the large network will tend to outperform the small neural network. Now, let's take a look at a contrasting view on neural network design as expressed in this paper, which is one of the most important and influential machine learning papers of this decade. In this figure, the authors train a plain 20-layer and a plain 56-layer convolutional network on the popular CIFAR-10 dataset. They observe that not only does the test error get worse as the network is made deeper, which may indicate overfitting, but training error also gets worse. This behavior might be encapsulated in this graph here. Again, as depth increases, initially both training and test error get better, but then there comes a point at which both training and test error get worse. Now the question is, which of these views of neural network design applies in what situation? And if this view here in fact does apply in some or many situations, what can we do to avoid building networks that are too deep and are thus encountering this pathology where both training and test error are higher than necessary? This is one of the key questions we'll be addressing throughout this talk and hopefully make a good amount of progress on. This talk is structured as follows. We'll commence by introducing some deep learning basics. If you are an intermediate or advanced deep learning practitioner, I would recommend playing this video at twice the regular speed during this section of the talk. The talk has three main sections: how networks fail, why networks fail, and how to build networks that don't fail. By fail, we simply mean encountering this pathology here, where the depth of the network, the training error, and test error are higher than necessary. We'll end with a conclusion. Let's start with the deep learning basics. In this talk, we will focus our attention on feed-forward neural networks of this canonical form shown here. Each layer FL is a function depending on some trainable parameter theta L, as well as the latent representation computed by the previous layer FL-1. A formal definition of the types of feed-forward neural networks considered in this talk might be: a feed-forward neural network is a parameterized, continuous, almost everywhere differentiable function with fixed-size tensor input and output built up from layer functions via composition. In the bottom right, we show the design space for neural networks considered in this talk, i.e., the operations that we will use to build up layers and networks. Now, we will go through each of those operations. The only linear operation considered is the fully connected operation, where the incoming vector x is multiplied by a weight matrix W to yield the output Z. Each component of the output is connected to each component of the input, where that connection is weighted by the corresponding entry of the weight matrix. We initialize the weights in this matrix using standard initialization schemes. While we firmly expect the principles presented in this talk to also apply to the convolutional operation, formally extending the theory to and conducting experiments on that operation is future work. In this talk, we consider the following three nonlinearities: ReLU, which is arguably the most popular nonlinearity in research and practice; TAN, which is arguably the second most popular nonlinearity; and CeLU, which is a nonlinearity that was introduced at NIPS 2017 and has gained recent popularity. We use two different normalization operations: the popular batch normalization as well as layer normalization. Let's first consider batch normalization. Let Xin be the incoming matrix of latent representations for the current batch. Here, I ranges over the features and n ranges over the data points in the current batch. From each entry in that matrix, we subtract the mean over the data points in the batch at the respective feature, and then divide that entry by the standard deviation over the data points in the batch at the respective feature. The effect is that if we have a neuron whose activations are all over the place, after applying batch normalization, we have activations at that neuron that are centered on 0 with a unit standard deviation. Layer normalization is the counterpart of batch normalization, where the mean and standard deviation are taken over the features for each data point rather than over the data points for each feature. So for some data point, the activations at different neurons are all over the place. After applying layer normalization, those activations are centered on 0 and have a unit standard deviation. We combine these operations into layers and networks. We let each layer be composed out of, first, a fully connected linear operation, then a normalization operation, which can be either batch norm, layer norm, or none, where none corresponds to an absence of normalization, and finally a nonlinearity operation, which can be either ReLU, TAN, or CeLU. We stack big L number of layers, all of which have the same form, except the last layer, which does not have the nonlinearity operation. The final output of the network is either the output of the last normalization operation if it is batch norm or layer norm, or the output of the last fully connected operation if normalization is absent. In this architecture, the trainable parameter theta L of each layer L corresponds to the vector of entries of the weight matrix of the fully connected linear operation. In addition to the linear style of connectivity, we also consider sked connections as used in ResNet. Here, the output of each layer is fed into two different computational units, the skip block S and the residual block ρ. They compute different outputs, which are then added together to form the output of the next layer. We consider three datasets in this talk. The MNIST dataset, where images of digits are mapped to digit labels, CFAR10, where images corresponding to 10 object categories are mapped to category labels, and white noise, where randomly generated white noise images are mapped to randomly generated white noise labels. We will train our neural networks using the simplest and most popular formalism. We start by evaluating the network F with the stored parameter theta at some data input x to obtain the corresponding output z. Second, we evaluate the arrow function at the output z and the ground truth label y. Third, we compute the gradient of the arrow function with respect to the output z. Then we backpropagate this gradient through the network to obtain the gradient g theta with respect to the parameter. We process that gradient g theta with an optimizer. For example, stochastic gradient descent corresponds to multiplying a constant c known as the step size to the gradient g theta. Finally, we subtract the process gradient from the stored parameter theta and start again with step 1. This formalism as shown here corresponds to training with a batch size of 1. Of course, in reality, we might have a batch size larger than 1. This corresponds to carrying out these 6 steps in parallel for multiple data points x, y, and then subtracting the resulting g theta prime vectors from theta simultaneously. Let's see what that training formalism looks like in practice. Consider a randomly initialized neural network of depth 10 using ReLU nonlinearities and batch normalization. We use 2-class MNIST, a subset of MNIST containing only 1s and 2s. Hence, our network has 2 output neurons. Here, we plot the output of the network. On the x-axis, we plot the value of the first output neuron corresponding to class 1. On the y-axis, we plot the value of the second output neuron corresponding to class 2. We take each of the approximately 12,000 data inputs and propagate them forward through the network, obtaining approximately 12,000 outputs. Each of those outputs is plotted in this graph here. In this region of space, the class 1 neuron has a higher activation than the class 2 neuron. And in this region of space, the class 2 neuron has a higher activation than the class 1 neuron. Therefore, data inputs mapped to this region of the output space are classified as 1, and data inputs mapped to this region of output space are classified as 2. We can look at individual data inputs. This one here, which is mapped to this location in the output space, is correctly classified, whereas this one is incorrectly classified. Similarly, this 2 is incorrectly classified, whereas this 2 is correctly classified. Now let's say we would like to conduct a training step with this data input here that was incorrectly classified as a 1. Let's say that the negative gradient of the arrow with respect to the output is pointing in the direction of the space where that data input would be correctly classified as a 2. Stochastic gradient descent dictates that if we change the parameter theta with a small enough step size, then the output will indeed move in the direction of this negative gradient. And this is precisely what we find if we apply a small step size. With the step size 1 times 10 to the minus 5, the output moves slightly in the direction of the negative gradient with respect to the output. If we choose a step size of 5 times 10 to the minus 5, it will move substantially in that direction and into the desired region of space. If we keep increasing the step size beyond this point, the output will start to move pseudo-randomly across the space. And by the time the step size reaches 2 times 10 to the minus 3, it will have moved over here, which is a point that has absolutely no relation to the original output or the gradient with respect to the output. This behavior, where small step sizes correspond to movements in the correct direction, whereas large step sizes correspond to pseudo-random movements, is a very important behavior that will come up soon again. Now we move to the first main section of the talk, how networks fail, and we'll start with the exploding gradient problem. We will analyze this problem in significant detail, whereas we will explain the other two problems more briefly. To illustrate the exploding gradient problem, we will use decision surfaces of neural networks. When we take this single input and feed it through a network of a given architecture, the output depends on the value of the parameter theta. To generate a decision surface, we choose a two-dimensional subspace of the parameter space and depict how the output of the network corresponding to this input varies as the parameter value varies within this subspace. The parameter subspace we choose is a sphere. Specifically, we take 3 randomly initialized parameter values theta, theta prime, and theta double prime, and consider the sphere centered on the origin containing those 3 parameter values. Here we are showing the decision surface of a 10-layer batch norm ReLU network on 3-class MNIST containing images of 1s, 2s, and 3s. The output space of the network is shown here. Since this is a network for 3-class MNIST, it has an output layer with 3 neurons. That is, it produces a 3-dimensional output vector. We normalize the length of that output vector so that it lies on the unit sphere. That unit output sphere is shown here. If the normalized output lies in this region of the sphere, it shows up as red over here. If it lies in this region of the output sphere, it shows up as blue over here. And if it lies in this region of the output sphere, it shows up as green over here. each parameter value in this space is represented by the color of the output space at the location this input is mapped to. Each color corresponds to a class label. Each of those colors are associated with class label 1, each of those colors with class label 2, and each of those colors with class label 3. As usual, class labels are assigned based on which component of the output vector has the largest value. Both the sphere of parameter values, as well as the output sphere, are depicted as azimuthal projections. We find that for the 10-layer batch-ReLU network, the complexity of the decision surface is quite high. As we move through the parameter space, colors switch rapidly, and therefore labels switch rapidly as well. In other words, a small perturbation to the parameter value leads to a large change in the output that this input is being mapped to. How does this relate to the exploding gradient problem? In a deep network, the complexity of the decision surface can increase exponentially as we consider parameter subspaces corresponding to lower and lower layers. For a depth 50 ReLU batch network, if we vary only the parameter in the highest layer, theta 50, we obtain a very simple decision surface. As the parameter changes, the output changes very slowly. This is not surprising, given that the output is almost a linear function of theta 50. Here is what happens if we vary the parameter of the second highest layer only. Fifth highest layer, 10th highest layer, 20th highest layer, and the lowest layer. As we can see, the complexity of the decision surface increases drastically as we move away from the output layer. How can we measure the complexity of the decision surface? The complexity is, roughly speaking, the number of times we cross the output space as we cross the parameter space, i.e., the number of times we switch color as we move across this sphere. Here, we show a path in parameter space as a red line, and the approximate corresponding path in output space as a red curve. We can quantify the length of the red curve as the speed at which the output changes relative to the parameter, normalized by the size of the output space and the size of the parameter space. So if, say, the output changes at a rate of 100 as we move across the parameter space, and say the output space has diameter 10 and the parameter space has diameter 5, then we could traverse the output space 100 times 5 divided by 10 equals 50 times as we traverse the parameter space. And that would lead to on the order of 50 color changes. We formalize this with what we term the gradient scale coefficient. The GSC is the Frobenius norm of the Jacobian of the output of the network with respect to the latent representation computed by layer L, normalized by the length of the output, the length of the latent representation, and the square root of the dimensionality of the latent representation. The GSC is a measure of the number of times the output space is crossed when crossing the space of latent representations FL. It is a measure of the complexity of the decision surface with respect to the parameter of the lth layer. Instead of using the output f of the network to define the GSC, we can also use the value of the arrow function e, which is itself a function of the output. Now we say a neural network exhibits exploding gradients with rate r and intercept c if the gradient scale coefficient can be closely approximated by cr to the big L minus small l. Let's take a look at 7 different architectures. ReLU without normalization, ReLU with layer normalization, ReLU with batch normalization, TAN, TAN with layer normalization, TAN with batch normalization, and CeLU. We consider randomly initialized depth 50 networks that have a width of 100. The data is white noise. As we can see, the gradient scale coefficient behaves very differently for different architectures. For 4 architectures, batch ReLU, batch TAN, layer TAN, and CeLU, the GSC increases almost perfectly linearly in log space as we move away from the output layer. This corresponds to gradient explosion. Batch ReLU has the highest explosion rate and CeLU the lowest explosion rate. In contrast, the other 3 architectures, ReLU, layer ReLU, and TAN, do not exhibit exploding gradients. However, this comes at a cost, as we will see later in this talk. To verify that the gradient scale coefficient actually measures the complexity of the decision surface, we plot it for 3 different layers in different architectures. For the 41st layer in a depth 50 batch ReLU network, for the 30th layer in a depth 50 layer TAN network, and for the 4th layer in a depth 50 CeLU network. The GSC has similar levels in all 3 cases. While the visual features of the surfaces differ in, for example, the sharpness of color boundaries, the level of complexity is comparable. Now we will show how gradient explosion leads to high errors and thus to what is termed the exploding gradient problem. This is the most complicated section of this talk, and so we will break it down into 4 steps. We will begin by showing that exploding gradients cause small update sizes. Again, we turn to the decision surface of a specific layer L. Let's say we wish to make a gradient-based update on the parameter of the Lth layer theta L using our familiar data input, and let's say that at time t, the parameter value theta Lt is at this point in parameter space. Because this data input is a 2, the negative gradient of the error with respect to the output might point towards this blue region of space. However, as you can see, if we want to be guaranteed to end up in a blue region after the update, we can only move a small distance in the direction of the negative gradient. If we move beyond this blue region, we might end up in a blue region such as this one or this one, but we might end up in a region of a completely different color, such as this one or this one. This ties back to what we showed in the deep learning basics section of this talk. Updating the parameter with a small step size leads to the output moving into the correct region of space, but using a large step size leads to a pseudo-random change to the output. Therefore, the size of the update that we can make decreases proportionally as the complexity of the decision surface increases. Let's confirm this experimentally with our 4 architectures that exhibit exploding gradients: batch ReLU, layer tan, batch tan, and CeLU. In this graph, we plot the inverse of the GSC as a dashed line, and we plot the estimated optimal parameter update sizes at each layer as little stars. Crucially, we plot the update sizes relative to the size of the parameter itself, and therefore relative to the size of the decision surface. For the 3 architectures with high explosion rates, batch ReLU, layer tan, and batch tan, as we move away from the output and towards the input layer, the update size decreases proportionally with the inverse of the GSC as expected. Keep in mind that our algorithm for determining these optimal update sizes was somewhat noisy. This algorithm also caused the artifact in the top right corner, where the inverse GSC is shown to decrease close to the output layer. The overall increase in the GSC for CeLU was too small to see a significant decrease in required update sizes across the depth 51 networks we used. These results were obtained on CFAR 10. Let's move on to the second step. We begin with the realization that an arbitrary network can be written as a residual network by introducing skip connections. Consider layer functions such as FL, FL plus 1, and FL plus 2. We can simply choose arbitrary, fixed initial functions IL, IL plus 1, and IL plus 2 to represent the skip block and define the residual functions RL, RL plus 1, and RL plus 2 as the difference between the layer functions and the initial functions to represent the residual block. However, there is one choice of initial function that stands out. Let theta L0 be the random parameter value from which we begin training, which we term the initial parameter value. If we set the initial functions to be equal to the layer functions at the initial parameter value, then the residual functions are the zero functions in the state the network is in at the beginning of training, which we term the initial state. This particular reformulation we term the residual trick. Of course, in the specific architectures we study in this talk, the elements of the parameter are equivalent to the entries of the weight matrices. We term the weight matrices in the initial state initial weight matrices, and we term the difference between the current weight matrices and the initial weight matrices the residual weight matrices. And now we find that as the relative update size decreases as we move away from the output layer, the size of the residual weight matrices, as measured by the operator norm, also decreases. This is unsurprising, as the residual weight matrices are simply the accumulation of the updates. And if the layer functions are well behaved, their size also decreases correspondingly. This completes step 2. We begin the third step by introducing the concept of effective depth, which was originally proposed by Veit et al. At NIPS 2016. Effective depth is the least amount of composition required for a close approximation of a deep network. Let's say we have a network of big L composed, parameterized, trainable layers. If we can replace this network with another network that yields approximately the same outputs but exhibits a lower degree of composition of trainable layers, then we say this network has the effective depth of the shallower network, which would be less than big L. There are two versions of the concept of effective depth. One version attempts to approximate the forward computation of the network, whereas the other attempts to approximate the gradient computation. In this talk, we will focus on forward effective depth. We can approximate a deep network via the Taylor expansion about the initial function. Consider a regular network written as a residual network via the residual trick. We will show how to compute the Taylor expansion recursively. We begin by computing the output of the first layer. Call this T1. T1 is fed into the initial function of the second layer I2. However, it is not fed into the residual function of the second layer R2. Instead, the output of I1 is fed into R2. We also add the product of the gradient of R2 with R1 to this sum. This corresponds to a first-order term in the Taylor expansion. The output of this computation is T2. We now simply repeat this motif. T2 is fed into I3, whereas R3 is fed by the initial functions. First-order terms of R3 with respect to both R2 and R1 are added. Rinse, repeat. The full definition of the Taylor expansion is given here. The core observation is that the Taylor expansion TL has a depth of 2 for all L. This is because composition with initial functions does not increase depth, as initial functions are fixed and thus do not co-adapt to other layers during training. No TL ever combines more than 2 residual functions via composition or multiplication. It only adds various terms with up to 2 residual functions together, as in an ensemble. We use the Taylor expansion to reduce the depth of our 4 exploding architectures in their fully trained state on CFAR10. We expand layers one after another, starting from the bottom layer. The depth reduction achieved through this is shown on the x-axis. As we might expect, we find that the smaller the residual functions, the more we can reduce the depth without increasing the error. This completes step 3. To complete step 4, and thus the argument as a whole, we go back to the Taylor expansion. While we only compose 2 residual functions at a time, we compose many initial functions. This corresponds to inserting additional, untrainable, nonlinear layers into the network that needlessly randomize the features. As a quick illustration of this effect, we consider ReLU networks of different depths. We train them on the MNIST dataset, but fix all but the highest layer throughout the training process. This corresponds to composing a single trainable layer with several untrainable layers, as in the Taylor expansion. we find that beyond adding a single untrainable layer, the performance rapidly declines. And this completes our argument. Observing the progression of the error throughout training on CIFAR-10, we find that the Cellu architecture, which exhibits the lowest gradient explosion, obtains the lowest final error. In fact, the performance of the architectures is ordered according to the level of gradient explosion in the initial state. Now we move on to the pseudo-linearity problem. Specifically, we turn our attention to the TAN architecture, which does not experience exploding gradients. In this graph, we show the quadratic mean of the activations of neurons after the linear operation in each layer. We find that this value decreases drastically with depth only for the TAN architecture. This means that activations in higher layers are clustered around 0, as shown here. Therefore, the TAN operation can be replaced with the identity function shown in red without incurring a significant approximation error. We call the general phenomenon of nonlinearity operations being approximately replaceable by linear operations pseudo-linearity. It is easy to see why pseudo-linearity is a problem. Assume the weight matrices, or indeed general linear operators, WL and WL plus 1, are separated in the network by a nonlinearity operation sigma that is approximately equivalent to some linear operator W sigma. Then we can combine all three linear operators into a single linear operator W prime. Therefore, the combined representational capacity of the two layers L and L plus 1 does not exceed the representational capacity of a single layer. Therefore, one of the two layers is redundant. Beyond the waste in computation and parameter storage this causes, redundant linear operators can degrade the conditioning of the network by causing, e.g., divergence of Jacobian eigenvalues, which can in turn lead to high errors. In this graph, we show the linear approximation error incurred at each layer when replacing the one-dimensional nonlinearity operation at each neuron with its best linear fit. The quantity we plot is 1 minus the ratio of signal powers between the approximated and actual neuron activations. We find that the TAN architecture is highly pseudo-linear, at least from the 10th layer onwards. Finally, we turn to the domain bias problem. Now we study the ReLU and layer ReLU architectures. In this graph, we show the standard deviation of the activations of neurons after the linear operation in each layer. We find that this value decreases drastically with depth only for TAN, ReLU, and layer ReLU architectures. This implies that activations corresponding to different data inputs become more and more similar with depth for those architectures. At first glance, we might suspect that pseudo-linearity does not apply in this case, because as the activations shrink, pseudo-linearity is prevented by the non-differentiability of ReLU at the origin. However, at closer inspection, we find that activations do not cluster around 0, but away from 0. Here, we show the activations at 10 randomly chosen neurons after the linear operation in the highest layer. At almost all neurons, activations are either entirely positive or negative, i.e., they are biased. This effect is what we term domain bias. We find that this behavior does, in fact, induce pseudo-linearity in ReLU-based networks, because the ReLU operation can be approximated by either the zero function, if almost all activations are negative, or the identity function, if almost all activations are positive. Referring to our graph from earlier, we find that ReLU and layer ReLU exhibit pseudo-linearity according to the linear approximation error. Note that the layer ReLU curve is shadowed by the ReLU curve in this graph. Here, we contrast the bias, standard deviation, and quadratic mean of the activations of neurons after the linear operation in each layer in a ReLU network. In this graph, we contrast the squared quadratic mean, squared bias, and variance. Of course, the former quantity is the sum of the latter two. And in this graph, we show the squared bias and variance as a fraction of the squared quadratic mean, which is the total signal power. We find that the relative power of the bias increases significantly with depth, especially in the early layers. Domain bias is a problem beyond causing pseudolinearity. Again, we turn to the decision surface for insight. Here, we show the surface as we vary the parameter of the first layer of a 50-layer ReLU network. As expected, domain bias causes the range of possible outputs to be concentrated in a very narrow range, as signified by the narrow range of colors visible. At first glance, the surface is very simple. However, as we heighten the contrast, we find that there are output oscillations of small amplitude. These necessarily arise because the output must shift as the parameter shifts. The smaller the range these shifts are contained in, the higher the quote-unquote frequency of these shifts, and the higher the surface complexity. And as before, a high complexity implies that gradients are only informative in a small region around the current parameter value, which leads to small residual functions and then high errors. Let us now summarize the entire How Networks Fail section. Gradient explosion leads to small residual functions, which in turn leads to low effective depth, which, when combined with nonlinear initial functions, leads to high error. Pseudolinearity leads to ineffective layers and thus to low effective depth and potentially high error. Finally, domain bias can lead to pseudolinearity and small residual functions, and then to high error via the mechanisms described above. We summarize the performance of our architectures on CFAR10. We observe that architectures with exploding gradients perform better the smaller the explosion rate in the initial state. Architectures with other problems perform badly overall. Now we move on to the next section of this talk, why networks fail. We introduce the nonlinearity coefficient NLC of a one-dimensional nonlinearity operation sigma and a real-valued random variable S. S represents the distribution of activations that are fed into the nonlinearity. It is induced by the distribution over data inputs. The NLC is the root of the expected square gradient, normalized by the ratio of the standard deviation of the activations before the nonlinearity and after the nonlinearity. The nonlinearity coefficient is a measure of how quote-unquote nonlinear a nonlinearity is for a given set of incoming activations. To illustrate this, let's look at some sample values of the NLC for some choices of sigma and S. Here, the nonlinearity sigma is shown in blue, and the distribution of S, which is always a Gaussian, is shown in red. A ReLU nonlinearity with a unit Gaussian has an NLC of about 1.21. The same is true for a ReLU nonlinearity with a narrow Gaussian. The NLC for ReLU is invariant under the multiplicative scaling of S with some positive constant because ReLU is itself invariant to such multiplicative scaling. When bias is introduced to the Gaussian, the NLC declines because ReLU will approach the identity function as the Gaussian attains a positive bias and the zero function as the Gaussian attains a negative bias. The more the bias increases relative to the variance, the closer the NLC gets to 1. Similarly, interpolating ReLU with the identity function reduces the NLC towards 1. The identity function, like all linear functions, has an NLC of 1. Tan with the unit Gaussian has an NLC of around 1.085, indicating that tan is in this sense more linear than ReLU. In contrast to ReLU, changing the variance of the Gaussian has a significant impact. We showed earlier how small activations lead to pseudo-linearity under tan. This is reflected in the NLC. Similarly, an increase in variance substantially grows the NLC. Finally, CeLU with a unit Gaussian has an NLC of around 1.035. Let's remember the NLCs of our three nonlinearities with unit Gaussians. Let's return to our familiar GSC graph. It turns out that the rate at which the GSC explodes in batch ReLU, layer tan, batch tan, and CeLU is almost exactly equal to the NLC. Hence, the rate at which the GSC explodes is very closely related to how nonlinear the nonlinearity is as measured by the NLC. This is intriguing. Let's dig a little deeper. We can rewrite the NLC by simultaneously multiplying and dividing the quadratic mean of the activations before and after the nonlinearity. We notice that the NLC is now a product of two terms. The first can be interpreted as the ratio of the domain bias after and before the nonlinearity, where the domain bias is measured by the ratio of quadratic mean and standard deviation. The second term is an expectation of the gradient normalized by the ratio of activation magnitudes. This can be interpreted as the gradient scale coefficient of the nonlinearity. This equation suggests that at a given level of nonlinearity, we should either see a commensurate growth of the GSC or a commensurate increase in domain bias. Let's investigate whether we can use the NLC to predict the behavior of architectures that exhibit domain bias rather than gradient explosion. Here, we show again our familiar bias standard deviation breakdown for the ReLU architecture. The key to making this prediction work is mean field theory, a theoretical model of randomly initialized neural networks recently introduced by Poole et al. At NIPS 2016. Under this model, we can predict the rate of domain bias increase, although the accuracy of the prediction is not quite as good as for architectures with exploding gradients. We can also simulate the value of the NLC at each layer. Because of increasing domain bias, we experience increasing pseudo-linearity, which leads to a decreasing NLC. Using mean field theory, we can obtain a powerful equality. The total nonlinearity of the network, measured as the product of the nonlinearity coefficients of the nonlinearity operations in each layer, is the product of the GSC at the input layer and the domain bias at the output layer, measured as the ratio of quadratic mean and standard deviation. To avoid pseudo-linearity, we must have NLCs significantly greater than 1. But under mean field assumptions, this must then lead to either gradient explosion or domain bias. This causes networks to necessarily suffer from at least one pathology we discussed in the How Networks Fail section of this talk. We obtain a three-way trade-off. The practical validity of mean field simulations for popular MLP architectures has been demonstrated both in this talk as well as in recent publications. We can tie this back to our decision surfaces. Gradient explosion manifests in the rate of change of color, whereas domain bias manifests in a reduction in the amplitude of the oscillations. Both manifest in an increased frequency of the oscillations, which is encapsulated in the NLC. Let's put it all together. In the left graph, we show the product of the empirical GSC growth and the empirical domain bias growth at each layer. In the middle graph, we show the NLC at each layer obtained via mean field theory-based simulation. In the right graph, we show the linear approximation error. The correspondence is clear. Note that the layer ReLU curve is shadowed by the ReLU curve in the middle and right graphs, and that the layer tan curve is shadowed by the batch tan curve in the middle graph. Can we justify the trade-off between pseudo-linearity, gradient explosion, and domain collapse without relying on one-dimensional nonlinearity operations? The answer is yes. Consider a function f that maps a random variable x from a domain curly x into a codomain curly f, which has the same dimensionality. Take an infinitesimal patch, marked in red, in the domain. Say f maps that patch to some patch in the codomain, shown in blue. It is easy to check that the difference in entropy between the blue and red patch is the logarithm of the absolute value of the determinant of the Jacobian of f at the red patch. Say we also have an incoming gradient gf at the blue patch. Then the corresponding gradient gx at the red patch is the product of gf and the Jacobian of f. Assume the orientations of gf and the Jacobian are independent. Then we can approximate the ratio of gradients with the normalized Frobenius norm of the Jacobian. And again, we obtain a powerful relationship. It turns out that the normalized Frobenius norm of the Jacobian is the quadratic norm of the absolute singular values of the Jacobian. This is at least as large as the geometric mean of absolute singular values. but the log of the geometric mean is precisely a multiple of the log determinant, which is equal to the normalized entropy difference. We can interpret this term as the gradient growth. We can interpret the entropy as the size of the domain, this term as the shrinkage of the domain, and the shrinkage of the domain itself as a generalization of domain bias. And we can interpret the gap between the quadratic mean and geometric mean as the degree of nonlinearity of f. Hence, to obtain both a small gradient growth and a small amount of domain shrinkage, the gap between the means, and hence the nonlinearity of f, must be small. We can view the ratio of expected means as the NLC of the multidimensional nonlinear function f. Let's summarize the why networks fail section. Under the theoretical models presented, nonlinearity must lead to gradient growth or domain bias. Too much nonlinearity leads to pathological gradient growth or domain bias, and thus to high errors. Too little nonlinearity leads to pseudo-linearity and thus to redundant layers, which can also lead to high errors. It is important to point out that while the theoretical models presented in this section enjoy predictiveness in popular MLP architectures, we leave open the possibility of designing new architectures that exploit the assumptions underlying these models in order to escape the three-way trade-off. Of course, in this talk, we can only scratch the surface of those theoretical models. We encourage readers to look at the references provided at the end of this talk and in the video description to gain a deeper understanding. Finally, how can we build networks that don't fail? We begin by explaining the power of skip connections in reducing the growth of the gradient scale coefficient. Let's say we have a layer function fl that is fed an incoming vector v and produces an outgoing vector fl of v. Doing backpropagation, fl receives an incoming gradient g and produces an outgoing gradient that is the product of g with the Jacobian of fl. We encode the lengths of the four vectors with variables a, k, b, and r in the way shown for reasons that will soon become clear. Let's look at the change to the GSC induced by this layer, specifically at the ratio of the GSC at the previous layer L-1 and at layer L. Note that we use the error instead of the prediction of the network to define the GSC, which, as we pointed out earlier, is also a valid choice. Plugging in the definition of the GSC, we notice that the Jacobian of the error with respect to the latent representation is simply the regular gradient g. Plugging in the lengths as specified, we obtain the value r. The length of the outgoing gradient vector beyond b over k signifies GSC growth. In this pictorial example, we chose r equals 1.2. Thus, the length of this vector is reflective of the behavior of, for example, a batch ReLU network which exhibits a GSC growth of around 1.21 per layer. Now we turn the layer function fl into a residual block and add an identity skip connection. Also, we assume that the outgoing representations and gradients produced by both blocks are uncorrelated and thus orthogonal, i.e., IEV is orthogonal to FL of V, and GI is orthogonal to GJ. In the forward direction, the outgoing length becomes A root 1 plus 1 over k squared, according to the Pythagorean theorem. In the backward direction, we obtain B root 1 plus r over k squared. K represents the ratio of the size of the skip block, which is A, and the size of the residual block, which is A over k. And now the ratio of the GSCs becomes 1 plus r minus 1 over k squared plus 1 plus big O of r minus 1 squared. We find that introducing a skip block that is k times larger than the residual block not just reduces the GSC growth by k, but by k squared plus 1. Therefore, skip connections are disproportionately effective at reducing GSC growth. This is caused by the Pythagorean theorem and shown pictorially here. For this example, we chose k equals 3. In general, adding an uncorrelated linear skip block to a residual block reduces the GSC growth induced by the residual block by approximately k squared plus 1, where k is the ratio of the size of the skip block and the residual block. We call this effect k-dilution. The disproportional effectiveness of k-dilution in combating GSC growth is arguably the primary reason for the success of ResNets at great depth. Let's confirm the effectiveness of k-dilution empirically. Recall the explosion rates we obtained for plane networks without skip connections. In ResNets, the GSC is indeed drastically reduced. Note the different scale on the y-axis between the two graphs. And note that we use ResNets with identity skip connections and residual blocks of depth 2, as is popular. We then went on to measure the k-dilution level at each block and multiplied the GSC growth rate obtained here by k squared plus 1 at each block. In essence, we corrected this growth rate by manually removing the dilution effect according to the theory we outlined. We find that this causes the GSC to grow again almost linearly in log space at rates very similar to those of corresponding plane networks. Therefore, the theory of k-dilution is indeed predictive. We trained 5 ResNet architectures on CFAR10. Unsurprisingly, they outperformed all plane networks except CELU. It is worth knowing that the amount of k-dilution in a block can be easily controlled by using scaling constants to increase or decrease the size of the skip block or residual block in a ResNet. If a block is k-diluted, scaling the skip block with a constant c causes it to be ck diluted. Scaling the residual block with a constant c causes it to be k over c diluted. It is important to remember that in most practical ResNet architectures, introducing constants at a single block has knock-on effects on the dilution level of other blocks. ResNet reduces GSC growth through k-dilution, and hence through linearization. As we saw in the why networks fail section of this talk, another way to linearize a network is to simply choose a nonlinearity with a lower NLC. And as we also saw, we can reduce the NLC of ReLU by increasing the slope in the negative quadrant. This slope increase can also be interpreted as a weighted combination of ReLU and an identity skip connection that bypasses only the ReLU operation. At first glance, both strategies of linearizing, for example, a batch ReLU network, should yield equal training success. There is, however, a key difference between the two approaches. Introducing the skip connection does not affect the NLC of the trained component of the network. Because the skip block is untrained, it is part of the initial function when the residual trick is applied to the network. The skip connection does not affect the representational capacity of the trained residual function. In contrast, the altered ReLU operation lies on the same path as the trained parameter. Therefore, it linearizes both the untrained initial function and the trained residual function equally. Correspondingly, we see a large performance difference between ResNet batch ReLU networks and plain batch ReLU networks with altered ReLU operation when training on CFAR10. As the slope in the negative quadrant of ReLU varies, we obtain an error minimum. However, the error achieved by ResNet is more than an order of magnitude smaller. We formalize the principle of k-diluting specifically the initial function in what we term the orthogonal initial state. A network achieves an orthogonal initial state if the initial function multiplies the incoming vector with an orthogonal matrix OL. The residual function, of course, is initially the zero function. By choosing a significantly nonlinear residual function, we can achieve both a relatively low overall GSC and a relatively high representational capacity. Note that achieving the orthogonal initial state only approximately, as ResNet does, can still confer significant benefit. While the orthogonal initial state does not circumvent the three-way trade-off between nonlinearity, gradient explosion, and domain bias, it recognizes that nonlinearity specifically contained in the initial function contributes very little to the modeling capacity of the network. Thus, it removes relatively unnecessary nonlinearity. Let's look at another method for attaining an approximate orthogonal initial state. The Lux linear initialization for ReLU MLPs introduced by Balduzzi et al. At ICML 2016. We split the neurons in each layer into two equally sized groups. Then we draw a uniformly random orthogonal matrix O of dimensionality equal to half the dimensionality of the layer. The weight matrix is then initialized using 4 tiles as shown here. In the initial state, the entire network shown here becomes an orthogonal transformation of the input X. During training, the tiles in each weight matrix vary independently as in a regular ReLU network. Here, we compare the performance of a Lux linear initialized ReLU network on CFAR10 with that of a ReLU network where weight matrices are initialized as a single uniformly random orthogonal matrix multiplied by the square root of 2. Again, we vary the slope of ReLU in the negative quadrant. And again, there is an ideal value for the slope. And again, the network with an approximate orthogonal initial state significantly outperforms even that lowest error value. In fact, Luck's linear initialized ReLU attained the lowest error of all MLPs of depth 51 we trained on CFAR 10 as part of our research. Finally, we conclude. We found that the view of neural network design that posits an increasing training and test error with increasing depth generally holds true, at least for networks with fully connected layers, assuming that, roughly speaking, the degree of nonlinearity of each layer or block is approximately constant. We derive the following practical design principles for neural networks. Eliminate untrained nonlinearity specifically contained in the initial function by using an orthogonal initial state. We presented two methods for achieving this: ResNet and the Luck's linear initialization. Avoid excessive total nonlinearity. This can lead to exploding gradients or domain bias, to low effective depth, and to high error. Avoid insufficient total nonlinearity. This can lead to underfitting. Avoid pseudo-linearity. This leads to redundant layers and can also lead to high error. If the GSC does grow significantly as the gradient backpropagates, it may be worth adjusting the step sizes used for each layer so that the size of the update on the parameter relative to the current size of the parameter decreases in proportion to the inverse of the GSC. Finally, the total nonlinearity can be controlled, for example, by controlling k-dilution by multiplying fixed constants to skip blocks or residual blocks in resonance. A good high-level summary of this talk is given in this illustration. These graphs juxtapose the classical view of the behavior of machine learning models as represented by a Gaussian kernel machine with the behavior of deep networks. Note that these illustrations do not depict experimental results. In both cases, the number of parameters in the model grows linearly with the number of kernels k and the number of layers L respectively, assuming the width of the deep network is constant. In the Gaussian kernel machine, however, we experience the curse of dimensionality, which causes the complexity of the function computed by the model to scale as the dth root of the number of kernels, where d is the dimensionality of the data. In contrast, the complexity of a deep network scales exponentially with depth, assuming that the degree of nonlinearity of each layer is roughly constant. The red curves illustrate the case of 10-dimensional data and a gradient explosion rate of 1.2 respectively. Many open questions remain. While we firmly expect our analysis of neural networks based on fully connected linear layers to extend to convolutional neural networks, we have yet to perform an in-depth analysis. Also, we expect the theoretical models presented in this talk to be somewhat less predictive in the case of convolutional networks. Similarly, what about recurrent nets? Much of our analysis was based on the properties of networks in their randomly initialized state. It is an open question how the evolution of properties such as domain bias, explosion rate, and NLC during training impacts training success. Also, it is an open challenge to build predictive theoretical models of trained networks. We have focused our analysis in this talk on training error. Undoubtedly, the pathologies we discussed have a profound impact on the generalization gap as well. While we have presented important principles for neural network design, we are working on converting those abstract principles into concrete, off-the-shelf methods that optimize architectures and training algorithms according to these principles. Finally, escaping the three-way trade-off between pseudo-linearity, exploding gradients, and domain collapse may be possible by designing architectures different from contemporary popular architectures that exploit the underlying assumptions of the theoretical models presented in this talk. This talk is based on the publication The Exploding Gradient Problem Demystified: Definition, Prevalence, Impact, Origin, Trade-offs, and Solutions. It is freely available on archive.org. The link is shown here and is available in the description of this video. The talk also draws from a publication that is currently under development and is projected to be released in May 2018. Upon release, the link to this publication will be added to the video description. The other references are shown here. Links to those publications, as well as hyperlinks that take you directly to specific sections of this talk, can also be found in the video description. I will present an earlier version of this publication at the 2018 installment of the International Conference on Learning Representations. Hopefully, I will see you there, and thank you for watching.